bearing capacity. So the bearing capacity that will be considering is the bearing capacity of driven piles. Okay. Now we have basically two conditions when we consider the bearing capacity of driven piles. The first condition is if the soil in which the pile is being driven into is a cohesive soil, and then the second condition is if the soil is a cohesionless soil. Now, if the given soil is a cohesive soil, we have our bearing capacity to be given as Cu times Nc times AB, where this is our cohesion. Okay, it can be drained or undrained. This is our bearing capacity factor. This is our area at base. We have alpha times Cu times As. Now, whenever our soil, the soil in which the pile is being driven into, is a cohesive soil, this is the expression we use to find our ultimate bearing capacity. And secondly, if our soil, the soil being considered is a cohesionless soil, then this is the expression we use to determine our bearing capacity. So some of the parameters in here are not given in the particular problem. So these are some expressions in which we use to find the given parameters. So we'll be taking a question. So the question says, a concrete pile driven into a dense sand has the following parameters: diameter to be 25 centimeters, unit weight gamma 18 kilonewton per meter cube. We have KS to be 1.0. We have phi to be 32 degrees. We have the depth to be 6 meters. It says calculate the ultimate bearing capacity of the pile. Take NC to be 45 and our deflection to be 0.555. The second part says using the same parameters in the above question, but in a clay deposit, take Cu to be 30 kilonewton per meter square, alpha to be 0.62. Calculate the allowable load. Take factor of safety to be 3. All right. Now, these are the given parameters from the problem we are considering. Now, what is the first thing that we need to note before we solve this kind of problem? Is the kind of soil. All right. So if we check the given problem, it says a concrete pile driven into a dense sand. Now, a sand is a cohesionless soil. Okay. So whenever we talk about sands, gravels, they are cohesionless soils. When we talk about clay, those are cohesive soils. Hence, because we know that it is a dense sand and it is a cohesionless soil, our ultimate bearing capacity will be determined using this expression. All right. So we have, okay, this to be our ultimate bearing capacity. We have ultimate bearing capacity Q. So we are solving the first part of the problem to be equal to P subscript D times NQ, right, times AB, A at base, okay, plus KS sigma V prime and delta AS. All right. Now, from this given problem, from the given parameters, we don't have this expression. Okay. So our first task will be to determine the unknown parameters in this equation. So let's start with U subscript D. Okay. We have this to be given as what? Gamma L. What is our gamma? Our gamma is 18 kilonewton per meter square, meter cube, and our length is 6 meters. Hence, this is equal to 18 times 6. And that will give us what? (108 kilonewton per meter squared? Okay. The next thing we have to find is our effective area at base, which is given as pi d squared over 4, and that is equal to 3.142 times our diameter is given in cm. we have to convert it to meters. So that is equal to 0.25 squared all over 4. And we have this to be equal to what? 3.142 times 0.25. We are converting the diameter of the pile from centimeters to meters. Okay, divided by 4. That will give us 0.045 meter, 0.049 meter square. Okay, the next thing we need to determine, so in this expression, okay, we have gotten this, right? We don't have this, which is the bearing capacity factor. We have gotten this. Do we have the value of PS? Yes, we have it to be 1.0. We have the value of our delta. Yes, we have it to be 0.55 times 5. And then next thing is to find our delta. So our delta is going to be what? 0.55 times our phi. And our phi is given as what? 32 degrees. So times 32, that's 17.6 degrees. But now in the expression, what we have to get is what? Tan delta. Alright? So tan delta is going to be equal to tan of 17.6 degrees. And that will give us what? Okay? So tan delta, which is tan of this, so this is our delta. That will give us what? 0.31. Alright. Let's get our S, and that is giving us what? Pi dl, which is equal to 3.142 times, converting our diameter from centimeter to meters, 0.25 times our length, which is 6 meters, 6. That will give us what? So 3.14, which is our pi, times our diameter, 0.25, times our length, 6. That will give us 4.71 meters. So we have this, we have this, we have this, we have this. Okay. Okay, we haven't gotten an expression for this. We have this. So our next task will be to determine this value. Right. So sigma v prime is simply equal to what? All over 2. This substitute v all over 2. And this is giving us what? 108 kilonewton per meter square. Is 108 divided by 2. And that will give us what? That will give us 54 kilonewton per meter square. Alright. Now, how do we get this bearing capacity factor? For us to get our NQ, which is our bearing capacity factor, we need to head over to the bearing capacity table, where we'll be making use of our phi. So if we head over to our bearing capacity table, which we can see, okay, our bearing capacity table. So we are given a phi, okay, of what? 32 degrees. All right. Okay, so on the bearing capacity table, okay, bearing capacity factors table, we are giving our phi to be what? We have our phi to be what? 32 degrees, right? So for 32 degrees, do we have, on that table, do we have 32 degrees? So we don't have 32 degrees. Hence, we are going to carry out what? Interpolation to determine the value of NQ, which is the bearing capacity factor for 32 degrees. So we have between 30, before and after 32, we have 30 degrees, right? We have 32 degrees, and then we have 35 degrees. So for 30 degrees, we have our NQ to be given as 12.7. For 32 degrees, we have our NQ, which is what we are looking for. And then for 35 degrees, we have our NQ to be 22.5. Okay, at 30 degrees, 22.5. And at 35 degrees, this is 41.4. So we carry out interpolation. So we have 32 minus 30 all over 35 minus 30 is equal to NQ minus 22.5 all over 41.4 minus 22.5. So 32 minus 30, we have 2 all over 35 minus 30, 5 is equal to NQ minus 22.5 all over 41.4 minus 22.5 will give us what? 18.9. Okay. So at this point, we can simply cross multiply. So 2 times 18.9 will give us what? 37.8 is equal to 5 times NQ, give us 5 NQ, okay, minus 5 times 22.5. This will give us 112.5. Alright, so at this point, we simply cross this 112.5 over to the right hand side. So we have 37.8. Crossing this over, it becomes positive, plus 112.5 is equal to what? 5 NQ. Okay, so at this point, if we make NQ subject of the formula, we have our NQ to be equal to 37.8 plus 112.5 to 150.3 all over what? 5. And that will give us what? That will give us 30.06. That was 30.1. Hence our NQ is equal to 30.1. So having been able to determine all the parameters, we simply substitute in to get our ultimate bearing capacity for the cohesionless soil. So our ultimate bearing capacity QU is equal to, what is our P subscript D? We have this to be what? 108 times our NQ, which is 30.1, times our effective area at the base, A subscript B, which is what? 0.049, plus our KS is given as 1.0 times our sigma V prime is given as 54 times 54 times, what is tan delta? Times 0.31 times our surface area A subscript S is what? 4.71. That's equal to what? 108 times 30.1 times 0.049 plus 1.0 times 4 times 0.3 times 4.71. That will give us 236.238.1.14 kilonewton per meter square. All right. So that's the first part of the question. So the second part of the question says using the same parameters in the above question, but for a clay deposit, C equal to 30 kilonewton per meter square and the rest, calculate the allowable load. All right. So for the second part, it says for a clay deposit. Now, our interest first is the kind of soil. Because it's said for a clay deposit, it is simply a what? A cohesive soil. Hence, our allowable load, QA, is our ultimate load, okay, divided by factor of safety. So what is our task? Is to get the ultimate load, which is the ultimate bearing capacity of a cohesive soil, and then divide that value by the given factor of safety to obtain our what? Allowable load. Okay, now, so what's the first thing we determine? The first thing we determine is to determine our ultimate bearing capacity. So from the given expression, we have CU, all right? We have um we have calculated our AB. We are given our addition factor, which is alpha, to be 0.62. We have our factor of safety, and then we are also, okay, so we are also given our NC to be 45 from the first problem. So our next step, since we have all these parameters, is to compute the ultimate bearing capacity. Hence QU, which is for a cohesive soil, is simply equal to our CU, which is what? 30 times our NC, which is what? 45 times our A subscript V, which is what? 0.049, all right, plus our addition factor alpha, which is 0.62 times our CU times our AS, and our CU is giving us 30 times the last expression AS, which is what? Times 4.71. Hence, this will give us what? 153.76 kilonewton per meter. Hence, our allowable load is equal to QU all over factor of safety, and this is equal to 153.76 all over 3, which is our factor of safety. That will give us what? 51.25 kilonewton per meter. So this is how to find the ultimate bearing capacity for a driven pile, whether for a cohesive soil and for a cohesionless soil.